American Airlines required that the total outside dimensions, length plus width plus height of a checked bag not exceed 62 inches. Suppose you want to check a bag whose height equals its width. What is the largest volume bag of this shape that you can check on an American flight? We're looking for the largest volume, meaning that we need to maximize the volume. We would need the function for the volume. Since this is a bag that has the length, width, and height, we assume that it is a rectangular shape whose volume is the length times the width times the height. We're also told that the height equals the width, where h equals w. So instead of having length times width times height, we can have length times width because the height equals the width. And so this is now L times W squared as the volume. This will be our objective equation. The constraint is that the length plus the width plus the height has to be less than or equal to 62. It cannot exceed 62. This means the constraint equation will be L plus W plus H less than or equal to 62. But again, the height equals the width, so this is L plus W less than or equal to 62, or L plus 2W less than or equal to 62. Isolate L, we have L less than or equal to 62 minus 2W. Although this is an inequality, for the purpose of getting rid of one of the variables in the objective equation, we assume that this is equality for now. The volume equals the length is 62 minus 2W times W squared. Multiply this out, we have 62W squared minus 2W cubed. This is the objective volume function. The length, the width, and the height have to be positive. And by looking at this objective equation, we see that W cannot be over 31, because if it is over 31, then 2 times 31 will be more than 62, which will make the negative length, which is not good. This is the domain of the function. We then find the critical point by taking the derivative. This is 62 times 2W minus 2 times 3W squared using the power rule. The derivative V prime is 124W minus 6W squared. We then set this derivative equal to 0 and solve to find the critical point. We can factor out 2 and W. What we have left for the first term, 124 divided by 2 is 62. And 6 divided by 2 is 3. And we factor out W already. This is a zero product, so we set each of the factor equal to 0 and solve for W. W equals 0, or 3W equals 62. W equals 62 over 3. The unit is in inches. Now we cannot use 0 because if the luggage has a width of 0, then it doesn't have any volume, so we can ignore this W equals 0 solution. We will use W equals 62 over 3. But since the height equals the width, the height is also 62 over 3. The length is 62 minus 2 times W, but W is 62 over 3. This is 62 minus 124 over 3, which is 62 over 3. We will conclude that to obtain the largest volume, given the configuration of the checked bag, we would need the width to be 62 over 3 inches, the height 62 over 3 inches, and the length is 62 over 3 inches. And so this is a square box. 62 over 3 is approximately 20.67. Now, how do we know that this combination of dimension will give us the largest volume? We use the first derivative test. W equals 62 over 3 is a critical number. This is approximately 20.67. Pick a number between 0 and 20.67. For example, W equals 1. If we plugged in W equals 1 into derivative, we will see that this is 124 times 1 minus 6 times 1 squared, which will give us a positive derivative. Pick any number after 62.3 such that W equals 21. Plug this into the first derivative, we will see that the derivative will be negative. What this means is that the volume is increasing and then decreasing, giving us the maximum value as 62 over 3.